Hello everyone and welcome to an overview of organic chemistry by me. I just decided to do organic chemistry because of how interesting the names of organic molecules were, and here are a presentation of my findings. First of all, I think we need to understand what organic chemistry is. Organic chemistry is a field of study that has to do with hydrocarbons. Hydrocarbons are molecules that contain the elements carbon and hydrogen. From the knowledge of organic compounds, scientists can help make pharmaceuticals, petrochemicals, food, explosives, paint, and cosmetics. Not all hydrocarbons are organic or natural. Some can be made by scientists. There are four main types of hydrocarbons: alkanes, alkenes, alkynes, and alcohol. There's something else called aromatic hydrocarbons, but those are usually not dealt with during 10th grade, so those were out of my area of studies or research. Organic chemistry allows us to understand the substances around us and how they interact. In addition to this, the molecules are named differently based on the number of carbons they have. For example, if the molecule has one carbon, the prefix is meth; if it has two, the prefix is eth, and so on. An alkane is a hydrocarbon with only a singular covalent bond. It has the general formula of CnH2n plus 2. Now you may be wondering, what's a single bond? Well, a single bond is a covalent bond that forms between two elements that share two electrons. In order for atoms to be stable, they sometimes share electrons between each other to form a noble gas configuration, which makes the element stable. In this case, carbon can share up to 4 electrons with other molecules, but it also needs 4 to become stable. In this formula CnH2n plus 2, n is an integer, so if you put in a number for n such as 1, the chemical formula would be CH4, or methane. There is an image of the first 10 alkanes with the names and chemical formulas of them. Now there is not only one way these alkanes can form or have a chemical structure. Sometimes the carbon might be sticking out in the middle of a chain, or it could just be a straight chain. Such as this, different compounds that have the same chemical formulas are called isomers. Because of the structural differences, the chemical and physical properties of isomers are different, and this includes all organic compounds. Saturated hydrocarbons are ones that have singular covalent bonds between them. Since alkanes don't have any double or triple bonds between the carbons, alkanes are examples of saturated hydrocarbons. An alkene is a hydrocarbon with one double bond and has a general formula CnH2n. As mentioned before, n is considered to be an integer because there cannot be a fraction of carbon or hydrogen. The minimum number of n in an alkene has to be 2. This is because in order to fit the definition of an alkene, there should be a double bond between carbons. A double bond is when elements or molecules share 4 electrons in total to form a covalent bond. There cannot be a double bond if there is only one carbon. Similar to alkanes, there are many ways that an alkene can be structured, and they are also called isomers. However, since they have double bonds, they are classified as unsaturated hydrocarbons. As can be seen in the image, there is only one double bond instead of 2, 3, or 4. The rest are all singular bonds. This is a very important piece of information to keep note because some students think that alkenes have double bonds only and draw double bonds, but that will make the organic molecule dysfunctional. An alkyne is a hydrocarbon with one triple bond and has the general formula of CnC2n-2. In this case, n is also an integer because there cannot be a fraction of carbon or hydrogen. The minimum number of n in an alkyne has to be 2. This is because in order for there to be a triple bond between the carbons, 6 valence electrons have to be present and bonded. But one carbon atom only has 4 valence electrons, or 4 electrons available for bonding, and there needs to be 6 valence electrons in total from 2 different carbon atoms in order to form a triple bond. Alkynes are similar to alkenes and alkanes in the fact that they are only carbons and hydrogens, but are unique because they have a triple bond that allows them to be classified as an unsaturated hydrocarbon. It is worthy of note that there is only one triple bond in the structure. So an alcohol is similar to hydrocarbons in the fact that there are carbons and hydrogens, but are not hydrocarbons because it has an oxygen atom in their structure. Instead of an hydrogen atom sticking out of a carbon or bonding with a carbon with a singular bond, the carbon bonds with a functional OH group, or hydroxide group. Since there is an oxygen in the molecule, the OH part becomes polarized or has different charges, which allows them to have a hydrogen bond between each other, which means that since they are charged, the electrostatic forces attract each other, each alcohols. Polarization can in a molecule can be achieved when there are different electronegativities or how much the elements wants the electrons. Since oxygen has the higher electronegativity than hydrogen, it pulls the electron slightly closer to itself, making a negative charge around the oxygen and a slightly positive charge around the hydrogen. This is what an alcohol is. It's an organic molecule that has hydrogens and carbons in it, but instead of hydrogen, it has a functional OH group that allows a hydrogen bond between the molecules, a very strong bond that relates to the boiling point of organic molecules. So using all the knowledge I've retained on alkanes, alkenes, alkynes, and alcohols, I was trying to conduct a lab. But since it's quarantine and I can't go out of my house to buy materials, and since the specific alkanes that I want are really rare sometimes, and I can't get it in its purest form, and it would be extremely hard for me to do a completely lab controlled experiment, I was just going to design a lab and get results from people who did similar labs, and I was going to compare the results between the boiling points of alkanes, alkenes, alkynes, and alcohols, all with the same number of carbon of 6 carbons. So it would be hexane, hexene, hexine, and hexanol. I was going to design a lab that could be able to check the boiling points of all of them, and I was going to compare the boiling points of them at different um, like when put in the same amount of heat. So for the background research, I think the information that I needed was types of intermolecular forces between the hydrocarbons and alcohols. So how each molecule interacts with each other, because boiling point does not affect the bonds inside the hydrocarbons, but rather the intermolecular forces such as dipole-dipole bonds or London dispersion forces. The strengths of forces between molecules and how that affects boiling point. So before we talked about how alcohol has a hydrogen bond because of the OH, um, but from what I've researched, it's much stronger than the London dispersion force between alkanes, stuff like that, and the 3D shape of molecules and how that affects boiling point. So there's different 3D shapes of alkynes, alkenes, and alkanes and alcohols. And those different shapes, the 3D models that they have, can affect the boiling point because some might be maximized to help increase the boiling point or decrease the boiling point, and some might be weakened because of their shape. So yeah, and I'm going to introduce you to the research I've conducted before the lab so that I can explain the results. There are only van der Waals forces between alkanes, alkenes, and alkynes. Normally, since there are only hydrogen and carbon in alkanes are generally not polar. However, since there are so many free electrons in the electron clouds that surround the molecule temporarily gains charges that allow it to attract to other molecules of the same composition. This is what a van der Waals force is. When electrons move around, they create negative charges toward the atom they go near to, and the place that they moved away from will have a positive charge. Since the electrons are moving so fast, the charges are present, which creates attractions between alkanes. This is the same for alkenes and alkynes. The double bond or triple bond present in alkenes and alkynes respectively does not disturb the path of electrons nor prevents it from creating temporary charges. It is worthy of note that these bonds are very, very susceptible to disturbance and cannot form a long distance between the molecules. This is because the force is so weak that when going further away from each other, the force would reach almost zero. The force is stronger, the electron clouds have a higher surface area because once they do, there's a higher chance that the electrons would be moving around more and creating more charge where the molecules interact with each other. To sum it up, if there is a higher surface area of electron clouds, there is a higher area for the molecules to bond with each other, which strengthens the bond overall. The only thing that is very important for the research that I did, or the lab that is going to be virtually conducted, is that a higher surface area of electron clouds can strengthen the bonds, and that the intermolecular forces between alkanes, alkenes, and alkynes are the same, van der Waals forces. For alcohols, it's a bit different, however. They have a functional polar OH group. As mentioned before, the polarity is caused by the fact that oxygen has a higher electronegativity, or greed for electrons. This causes them to pull the electron closer to them, making the oxygen side more negative and the hydrogen side more positive. Like charges repel and different charges attract. In alcohol, there is one OH group for each molecule, so the positively charged hydrogen from one molecule attracts the negatively charged oxygen from the other group, which creates a way stronger force than London dispersion or van der Waals forces present in alkanes, alkenes, and alkynes. The bond energy, which is the energy required to break down a bond, is way more for hydrogen bonding present in alcohol than how much energy it takes down to break down van der Waals forces between alkanes, alkenes, and alkynes. So we looked at the different bonds present in hydrocarbons and alcohols and the general strength of each of them. It was shown that only van der Waals forces existed in hydrocarbons such as alkanes, alkenes, and alkynes. However, a much stronger force exists for alcohols that have a functional OH group and can connect with each other through hydrogen bonding. This is because hydrogen bonding is a permanent big difference in polarity, which creates attractions, whereas van der Waals forces are continuously spontaneous and weak differences in polarity, which is a much weaker bond. The stronger the difference in charge is between the molecules, the stronger the bond strength is. And bond strength has to do with boiling point, because if there is a weaker bond strength, it will be easier to make the molecules boil by breaking the bonds between them, but more heat would be required. A higher temperature or more heat would be required to break the bonds in order to make them boil. So if there is a weak bond between the molecules, it will be easier to break down and will require less heat energy. However, if there is a stronger bond between each molecules, like alcohols or hydrogen bonding, then the boiling point will naturally be higher because it takes more heat in order to break those bonds down and boil the molecules. It was mentioned before how the surface area of the electron clouds affect the strength in bonding. However, the bond strength wouldn't be strong if the molecules cannot bond in a certain area due to the angle in which they are located. To explain, let's move to a drawing of hexene and one hexene, two molecules that we're going to look at in this lab. As we can see, hexane has a higher surface area for bonding than hexene does. Hexene cannot bond in the double angle because the bond is too weak. So what it does instead is it bonds to the longest side with the other hexene molecules. However, the surface area of that overall is less than the surface area of molecular interaction between hexane and another hexane, which results in a higher boiling point of hexane than it does for hexene. The bonds in hexane are stronger than the bonds of hexene because it has a higher surface area for interaction. 3-hexyne has a triple bond in the middle of the structure, which allows for a closer distance between the bonds. As mentioned earlier, van der Waals forces are affected by distance. By allowing the alkynes to be closer to one another by triple bonds, the strength of the bond increases. As mentioned before, if the strength of the bond increases, so does the boiling point. Therefore, if the 3D shape of a molecule makes it so that the molecule can have a stronger bond with each other, then the boiling point will be high. From this research that I conducted, it was shown that alcohol, the hexanol, has the highest bond strength because of its hydrogen bonding and also van der Waals forces present in them. Then hexyne, where it has a triple bond, which maximizes the bond strength between the alkynes. Then it was hexane because it has the highest surface area, a higher surface area than 1-hexene for bonding. So in conclusion, today we looked at what organic chemistry was, what alkanes, alkenes, alkynes, and alcohols were, and their physical and chemical properties, their general formulas and structures. We also looked at types of intermolecular forces between hydrocarbons and alcohols, strengths of forces between molecules and how that affects boiling point, and 3D shape of molecules and how that affects boiling point. The last 3 pieces of information or research that I conducted was for the lab that I was going to design, which relates with the boiling points of alkanes, alkenes, alkynes, and alcohols, all with the same number of carbon of 6. Hope you enjoyed the video, and I'll see you next time.